Hello and good day to whom may be watching this video. This video is a brief study on Stanford University's Central Energy Facility in part of an Energy and Architecture module based in Taylor's University. I'm Lai Kai-Xian and together with me is my partner Anson Ong Kah Kit. Let's dive into the study now. Located in Stanford, California, the Central Energy Facility is an integrated building with the higher education building type with Stanford U, having a 9,571 square feet and fully built and occupied on March 2015. Let's talk about the climate for a bit. Much of California has a Mediterranean-like climate and Stanford in specific has a more warm summer Mediterranean climate, meaning it has coldest temperatures of -3 degrees Celsius, while having average temperatures of 22 degrees Celsius, leading to a need of heating and cooling constantly throughout the year and even during the days. So, what is Stanford Central Energy Facility about? Its main intention was to be a new approach to meet energy needs for Stanford U. It creates and hosts a system that incorporates solar power and heat recovery to reduce greenhouse gas emissions, allowing the university to exceed the aggressive greenhouse gas emission reduction goals of California's landmark AB 32 Global Warming Solutions Act. This system helps eliminate 150,000 tons of carbon dioxide, which roughly equates to 32,000 cars. Oh, and this building is a zero net energy building. But what is that? Basically, it is a building combining energy efficiency and renewable energy generation to consume only as much energy as can be produced on site through renewable resources. But then, how and why did Stanford do this? This was all derived from a core issue based on a study done in 2008, comparing annual cooling and heating resulting in a shocking 75% heating and cooling overlap. Even looking at more detailed daily analysis of cooling and heating, energy use and annual analysis, about 70 to 75% of heat recovery potential by utilizing the heat produced by the chilled water system can be reduced to meet 80% of campus heating loads. This then produced an opportunity for efficiency and cost saving as well, especially in energy production and sustainability, as solar system can be used to power this system instead of fossil fuels. And all of these align with SESI, Stanford's Energy System Innovations, a project transforming the campus energy supply from one based on fossil fuels to one powered by renewable electricity, and through the facility meeting with SESI goals, reducing 63,500 metric tons of greenhouse gases, which is a 68% decrease in 2 years, saving 127 million gallons of potable water, a 67% reduction compared to average operations, and doing all this by saving $450 million over the course of 35 years. So, why does it work then? Let's talk about the Central Energy Facility and the systems affecting its surroundings. So, let's first look at the planning of the facility. The campus architect of Stanford University, recognizing that the campus would expand in the future in the direction of the new Central Energy Facility, or CEF in short, suggested that the new facility, specifically the office building component, be designed in relation to the long axis of Olmsted's historic campus plan, by placing the CEF at the end of one of these long axes. The structure would both terminate the axis and link it in an important way to the whole campus fabric. Well, then looking at the building envelope, it mainly consists of photovoltaic panels that span across the canopy tilted towards the east for maximum sunlight. These can also be observed with the sections, and the placement of this canopy and panels are also acting as massive shading devices for the active spaces inhabited by the people below. Therefore, the main renewable energy then resulted being solar energy, and also mainly due to the context of California, receiving large amount of sunlight but also due to it being installed en masse, and that caused a large overproduction of energy totaling to 175 kilowatts, which was able to be reused for the general campus, leading to now having about 53% of Stanford's total electricity use come from solar energy. The introduction of the PV panels will also part on helping to increase the efficiency and reliability, and even as viewed on the graph shown on screen, by introducing the PV as seen here, it is able to lower the campus electrical demands to help prevent any sudden non-renewable energy generation for the CEF as well. And finally, looking back at the building envelope, utilizing insulation minimum being R34 in the walls and R30 in the roof, and through the minimal exposures that lead to solar gain, the thick insulations and at least 3 inches of continuous insulation through exterior decks and studs, the building prevents thermal bridging, which is the prevention of conduction of heat throughout the building. Now, other than solar energy systems, CF also reuses and utilizes heating and cooling systems as well. I'll now pass the time to Anson to continue to elaborate on these systems.
Stanford relies on heat recovery process, meeting more than 90% of campus heating demands by capturing 2/3 of waste heat generated by cooling systems to produce hot water for the heating system. To make it possible, Stanford had replaced 22 miles of underground pipes and retrofitted 155 buildings on site. A key observation through SASE heat recovery with hot water system energy schematic was the 51% excess heat that could be capitalized. The building then also utilizing waste heaters, then to utilize trigeneration using power, heating, and cooling. The heat recovery and hot water generators, which requires more energy and heat, are placed nearby the solar panels to capitalize on those needs. The central energy facility, which also includes a high voltage substation, is run by a patented model predictive control software system developed at Stanford that optimizes cost and energy efficiency. The software has the ability to predict hourly campus heating, cooling, and the grid electricity prices 10 days in advance. We have been talking on how energy use. Then now, talk about how we maintain the central energy facility through the HVAC system. HVAC system includes heating, ventilation, and air conditioning. Radiant systems generally require less energy and provide greater comfort than all-air systems and are an ideal system for open spaces, mainly using radiation as a heat transfer method within the spaces, preventing weird pockets of coolness. The passive chill ceilings and seals reduce the cool wastewater within the building for the building, and these systems also help in reducing maintenance, energy use, and it is quieter than other cooling systems. An auxiliary system used throughout the building is a blanket type phase change material as a passive cooling technique, acting like thermal mass to absorb heat above a certain Q value and gradually become liquefied. Stanford applied active and passive strategies like user-operable windows, like large ceiling fans, focus on how the threads promote ventilation in the spaces, and assist HVAC system to spread the cooler air in the whole area in a short time. To sum up the HVAC system, Stanford applied active and passive strategies to assist central energy facility in ventilation, cooling, and determine how to operate in the most economical way. Right as we conclude, here is our studies with the post-occupancy evaluation of Stanford University Central Energy Facility. In the POE, we talk about how energy use, building positioning, and HVAC have impact on the users. Positioning the building to terminate along axis from the center of campus and create a strong visual presence at that termination. This then led to naturally more visitors, both from the campus and abroad. There was even a wedding in the outdoor amphitheater of Central Energy Facility, including classes and scheduled meetings held in the communal space to help understand about the CEF principles. Then, we talk about HVAC system. The automated system also plays a part in the user's evaluations, stating it was a simple but effective control of environmental temperature. The users preferred manual control only because they were concerned about the building's energy efficiency. The finely tuned system CEF has imposed that it is responsive to outdoor air conditions and efficiently reduced the heating and cooling load, also played a part of the user's daily comfort of CEF. Here is an annual and monthly energy use analysis to first understand how the CEF has affected and allowed the campus to capitalize on other energy use through heating and cooling other than just electricity. The electricity use is still the highest due to the harnessing of energy from the PV panels. Here is an overview of PV panel performance and net energy performance as well. This chart also showcases the amount of energy PV panels produced compared to the energy use of the building. Even in the lower sun times during the year, it still managed to match the energy use, showing how required energy from the building covered by half of the PV panels, resulting in Central Energy Facility being a net zero building, and in fact, net positive due to the excess of energy that it produced.
So, that's the end of our study and presentation for Stanford University's Central Energy Facility. Through this, studying the renewable energy system of the building and its effects to the whole campus in a large scale. We're also looking at the HVAC of the building in a smaller scale, studying how the building accommodates these systems efficiently. With that, thank you for watching this video, and we hope that it helped.